In computer science, a minimum spanning tree is the most efficient way to connect a network of vertices, ensuring the total weight of the connections is as small as possible. But building that tree becomes exceptionally difficult when no single machine holds a map of the entire system. Traditional approaches, like Kruskal's or Prim's algorithms, rely on a central coordinator. They require an eagle-eye view of the network to sort every edge weight from lowest to highest before making a single move. The Gallager-Humblet Spira, or GHS algorithm, eliminates the need for that coordinator. It provides a purely decentralized solution. In GHS, every vertex acts independently with zero global oversight, aware only of local connections. It requires a time complexity of O of n log n and a message complexity of O of m log n. N represents total vertices and m represents communication edges. Solving this means building the tree entirely from the ground up. The system must prove that purely local decisions can mathematically lock together into a perfect global structure without choking the network with excess messaging. The algorithm begins with an initialization phase. Every vertex in the network wakes up simultaneously and begins evaluating its immediate surroundings. Each vertex independently identifies the neighbor connected by the smallest weighted edge. Node A finds an edge of 5 leading to D. Other nodes do the same based on local minima. B and C select E. G chooses E, F chooses D, D chooses A. Once a node identifies its lowest weight path, it transmits a standardized Connect Me message along that edge. Because there's no central clock, these transmissions happen simultaneously. This creates structural anchors. When two nodes like A and D share the exact same minimal edge, they form a mutual connection. It is crucial to note that these initial pairings strictly obey local minimums. They make their choices completely ignoring the broader topology of the graph. This localized decision-making instantly organizes a chaotic field of independent vertices into preliminary subtrees. But it also introduces a critical algorithmic danger, the potential to form closed loops. In decentralized network routing, independent local decisions often create infinite loops, where paths circle back on themselves indefinitely. Look at this mathematical proof. 3 nodes, A, B, and C, form a triangle connected by unknown edge weights x, y, and z. If node A chooses x over z, x must be strictly less than z. If C chooses y, y is less than z. This sets up the critical architectural question. Is it mathematically possible for node B to select edge z, closing the triangle and creating a cycle? The answer lies in our inequalities. If x and y are less than z, z is the largest weight. Since node B only picks its absolute minimum edge, it can never select the heaviest path. It cannot choose z. This logic scales outward perfectly. It applies to any potential polygon, of any size, anywhere within the network. By mathematically forbidding the selection of a cycle-closing edge, GHS guarantees the network will organically assemble into a forest of discrete, open subtrees without global oversight. With cycles mathematically eliminated, the algorithm shifts its focus from individual vertices to these newly formed structural fragments, or subtrees. We locate the structural anchor of each subtree at the core edge, where two nodes mutually selected each other. A decentralized system cannot function with conflicting commands. To resolve this, nodes A and D merge computational authority, electing A as the leader. The exact method of breaking the tie between the two nodes, whether by comparing IDs or counting neighbors, is arbitrary. What matters is having exactly one leader per fragment. Because the network operates in parallel, this happens simultaneously. In an adjacent fragment, node C and node E perform their mutual election, designating C as the new leader. The newly elected leader is immediately assigned its primary objective, managing the subtree's next necessary outward connection. The leader now assumes total control over the internal topography and the message routing for its entire fragment. Leader election shifts the algorithm from microscale chaos into macroscale order. It transforms clusters of independent vertices into unified structural units, ready to negotiate with the rest of the graph. During the expansion phase, the leader must locate an outward path to merge its fragment with another, and do so without violating the cycle proof. The leader broadcasts a query ping down its internal edges to all nodes within its fragment. The query contains a strict condition. Internal nodes must only search for the lowest weight edge connecting to a vertex explicitly outside their current tree. To prevent cycles, nodes actively reject internal connections. Edges leading back into the same fragment are filtered out. Scanning valid external links, Node E locates two edges, sending back weights of 15 and 8. Node B performs the same scan. It locates external edges with weights of 7 and 9, transmitting that data up the chain. Leader C aggregates all options. Scanning the array, it calculates that 7 is the absolute minimum outgoing edge. Having found the optimal path, the leader authorizes the internal node holding that edge to initiate the connection. Node B executes the directive, extending a new, solid line across edge 7. This exact sequence, querying, filtering, analyzing, and connecting, occurs simultaneously across all leader-controlled fragments in the network. By routing all external intelligence through a single elected leader, GHS ensures that even massive, complex subtrees only ever execute mathematically perfect single-point outward connections. The algorithm is recursive. These subtrees continuously iterate the process, finding minimum outgoing edges, merging together, and electing new leaders for the combined structures. This brings us back to the core constraint of message complexity. In theory, a continuous loop of querying and reporting across thousands of nodes could easily overwhelm the network architecture, but there is a structural safeguard built into the math. In every single phase, a fragment must either double in size or merge entirely, drastically reducing the number of independent entities. The merges happen in distinct, massive levels. Because fragment size grows exponentially with each phase, the sequential merge levels are strictly bounded by the logarithm of n, the total vertices. Since the maximum number of phases is log n, the total network chatter is firmly capped. This proves the strict O of m log n message complexity. Isolated nodes, operating purely on blind local logic and hierarchical messaging, successfully engineer a globally optimal minimum spanning tree, and they do it without ever possessing a map of the whole.